I know, I like the notes that come from you because they're always colorful. Mine
Right?
Sad. Because I only have $8 left on printing.
That's like half a semester in this class. All right. So we're almost through this chapter on sampling and frequency domain, Fourier transforms, Fourier series, and all that. A lot of material here. There's a lot of fun stuff. Your homework is over part of it this week, and there'll be over more of it next week. It's, you know, it's hard to stress how important this stuff is enough. I think that it's hard because we can't in this class dwell on this material. But we could talk about this material for like the whole semester, really. So there's a lot in here, but we're kind of hitting the highlights as we go through, and I'm giving you guys, like, I don't want you to feel like it's like a watered down version. It's like the legit theorems and definitions, and you can apply them in many places. So what we're seeing is just a subset of the applications that you can use these things for. So one of the main topics of this chapter, though, is sampling, right? It's pretty key when you're taking measurements and getting data is sampling the data. And we learned last time how to construct a mathematical representation of sampling using those Dirac delta functions, if you recall, and that the strength of each Dirac delta function or pulse was representative of the value of the signal that we were sampling. And then we learned how to take the Fourier transform of that, and we learned that it essentially copies at the sampling frequency, it copies that Fourier transform representation over and over again throughout the spectrum. So you might have thought, well, I mean, that's cool or whatever, but like I don't really see the point of that. And today I'm hoping to convince you that this way of thinking, through sort of an example of how we can apply it, this way of thinking is really powerful, and it helps us see things that wouldn't have been obvious otherwise. So hopefully we can learn that today. So it's on Nyquist Sampling Theorem, Lecture 2.5, Aliasing and Reconstruction. When we sample a signal, we lose information. Just is that way. So if you think about it, a signal is a continuous quantity. A continuous signal is a continuous quantity. So you could sample it at higher and higher frequencies, and there would be data points in between. It's just like the real number line, right? There's always a real number in between two real numbers. So continuum thinking is always like a little bit of a falling off the edge of a cliff, right? Where you're like, oh my God, yes, it goes on forever. Yeah. Yeah. Yeah, and actually that's primarily the reason that we sample, right? Is to get a digital representation of a signal. We take data points and we put them into a computer, and it does things like integrates a function for us, or plots it for us, or does something else. I mean, we tell the computer how to do that for now until it starts telling us what to do. Yeah.
When sampling, is there a typical amount of inaccuracy? Is like sampling a population, for example, just as a different, is that going to cause inaccuracy or lack of precision necessarily?
Well, we're going to talk a lot about that in, I think it's next chapter, which is on probability and statistics. So the next couple chapter, we're really going to slow down and talk about the statistical ideas of it. What's enough data and all that.
Right. Something like if you sampled, your mom's cooking, a little taste of it's good, but you won't be able to tell how good it is until you actually taste it. So.
Right, and that's kind of what we're going to talk about today. And so if you represent your mom's cooking with a Fourier transform, then you can. There's actually a theorem that we're going to talk about that explains that tells you when you'll know. Well, actually, it doesn't tell you that. It tells you if you knew what the highest frequency component in the spectrum of your mom's cooking was, then you would know the minimum sample rate to sample at in order to reconstruct your system. The problem is that we never know a priori what the highest frequency in the sample in the signal is, and that's where that's kind of the rub on this. It's like
so there's a certain amount of uncertainty then.
There is a certain amount of uncertainty. Certainly. Okay. So when we sample a signal, we lose the information that's in between the sample points, right? It's just we do. However, we can reconstruct an approximation of the original signal if we make some assumptions about it. Okay. So this is Nyquist sampling theorem. If a signal has maximum frequency component F max, just it is sampled. Oh, no, there's a space there. I'm not really sure why there's no space. Should be a space there. If it is sampled at a frequency greater than 2 times that max frequency in the signal, it can be unambiguously reconstructed and otherwise not. We call Fn the Nyquist sampling, or the Nyquist frequency of a signal. So pretty much this is like we need to be sampling at a rate higher than that. And the max frequency component, the problem is we never know what the max frequency component is of a signal before we measure it, right? Kind of a catch-22. It's like, oh yes, well we'll figure out what F max is, and then we'll make sure we sample at that rate. But how are you going to figure out what F max is unless you measure it? So once again, we have one of these circles that is not. It can be vicious unless you take some precautions. So the not case, meaning it can't be unambiguously reconstructed, is characterized by aliasing, which is when a signal appears to have frequency components that are in fact higher than they appear, an artifact of sampling. This is the first time in our journey that Fourier analysis and frequency domain concepts will light the path. There are several ways to analyze aliasing, but perhaps considering the spectrum of a sampled sinusoid is the most accessible. So let's consider as in Figure 2.4, which is from previous lecture, the sampling of the function y of t equals cosine omega naught t, where omega naught is just some real number. The signal has the Fourier transform, as you might recall. Y of omega equals pi delta of omega minus omega naught plus pi times delta of omega plus omega naught, which is, if we were to remember what the sketch looked like, if this is the spectrum, there's a direct delta function of strength pi out at omega naught, and then there's a direct delta function out at of strength pi again at a negative omega naught. Okay. So this is just a pulse with strength pi at negative omega naught and one at positive omega naught. The Fourier transform y star of the sampled signal y star, different capitalizations, simply copies this pair of pulses to be mirrored about integer multiples of the sampling angular frequency omega s. So you all remember this, right? So this was our frequency spectrum for cosine omega t, and then omega naught t. And then if we sample it, remember we just take copies of this and we move it to every sampling frequency, about every sampling frequency. So that's why we've got like these pairs of colors, right? So omega and omega naught, this is a pair that is centered around 0. These yellow ones are a pair that's centered around what is the sampling frequency in radians per second, the angular frequency. And then there's a copy at every sampling, spaced out at the sampling frequency. So that's our Fourier transform. So according to, I don't know why that's not showing up, but this is, yeah, obviously issue there. Once again, cutting it a little close here, wasn't I? What it is I'm like, oh, you know, I could add this, and then like I'll like put that in, and then like I keep tweaking it, and last minute and stuff. So this is according to, this is the theorem here. So theorem 2.051. So theorem. That one, just the big red one right up here, or I guess dot one. According to the Nyquist sampling theorem, the sampling frequency has to be greater than the Nyquist frequency. Okay, it's required in order to avoid aliasing and allow us to uniquely reconstruct the original signal. Let's consider the situation in which the Nyquist sampling frequency requirements are met, as shown in the upper plot of figure 2.5. So that's this one right here. So we've got our Nyquist sampling frequency. We've got our sampling frequency is here. So these are the spaced out like that. So that's where we've got these pairs of pulses, right? So we've got our omega naught that's centered around 0, and then every sampling frequency interval we have another pair. Okay, and I color coded it so you knew which pair went with which. So the blue ones are centered here, the yellow ones are centered here, the magenta ones are centered here. I want to say the red ones are centered there, and the green ones are centered there. Okay. Now, so this is this top graph. This is when we are sampling with sufficient frequency, right? So this is good. But what's interesting is, say we are undersampled. So if we increased our the signal that we're measuring, if we increased its frequency up to omega naught prime, so from omega naught up to omega naught prime, that moves this guy over to there, right? Moves this out, and moves this guy over to there. So the blue ones went out, which means that the frequency of our signal increased, right? but we kept the Nyquist frequency the same and the sampling frequency the same, which means that now we're undersampled, which we know is a problem. Explain why it's a problem. Okay, so that's the problem. And then notice that this yellow pair over here started to encroach, right? This guy went over here. And then so does this one down here. This one encroaches on that interval as well. And notice how it encroaches. It completely mirrors what the other one looked like before. So in fact, if you wipe out the colors, these two look identical, and they're indistinguishable. So if I took out all the colors and I just put, they were all black. Yeah. Then you couldn't tell these two signals apart. And that's the situation we have when we sample this thing, because they don't come color coded, unfortunately. It's just like in a cell, everything's not like the Golgi apparatus isn't green, and the mitochondria aren't gold. It sucks. But like in the textbook, that's how it is. But unfortunately, in real life, it's not like that.
Well, since you can't really tell the difference if they've been swapped or not, how do we know that we've...
We don't. is what it comes down to. We don't know. If we did know, we would surely choose our sample rate to be high enough. But we don't know. So that is the question is, what do we do about it then? Since we got to sample stuff, and we know this is true. I mean, some people could have been like, I guess we don't do it. Like, I guess we're screwed, right? Like we're totally housed. But before we talk about ways to mitigate this, though, I wanted to mention this is the thinking of it in the frequency domain, and I think that this demonstrates it pretty well. You can also think about it in the time domain, and I didn't show an illustration of it, but the idea is that if you have the same points, if you want to, you can draw, I'm not even going to try to do it, but you can draw multiple sine waves that intersect those points. So it's not uniquely defined in the sampling frequency relative to the lowest. It's a similar argument, but I think this one's a lot easier to see. So that's why I used it. Okay, so that's that, and so we get this issue of these two spectra being indistinguishable, and so we don't know if what we're seeing, because when we do this sampling, we're going to see this line show up here. We're going to say, oh, does our signal really have a fundamental or does it really have a frequency? Am I looking at a cosine wave with a frequency of omega naught, or am I looking at a frequency of omega naught prime? We don't know, is what it comes down to. So what do we do? So it's important to note that once the signal is sampled, it's too late to do anything about it. So you're done. Like once it's sampled, you're stuck with it. There's no like magical reconstruction thing that you can do. You're screwed. But there are two ways to mitigate it, and they both happen before you sample it. The first is sample at a high enough rate to capture all the frequency components of the signal, which sounds great, right? You just don't know how. It's a problem. And step two, which is the sort of practical way, and this is what people actually do, and this is best practice, is to low pass filter, or also known as anti-aliasing filter, the signal before it is sampled. Not after it's sampled. If you do it after it's sampled, it's too late. Before it's sampled, so in analog, so this is almost always an electronic signal when you're measuring something. As we'll discuss, most of our instruments give us an electronic signal nowadays, and then we sample that electronic signal. And that electronic signal is analog, meaning it's a continuous signal until we start to sample it, right? we need an analog filter on that before we sample it. And this is something that I think we sometimes forget about because we're really used to now cheap digital electronics, right? And we think, we'll just reconstruct the signal after we sample it. Like that would be fine. We can filter it, which is true, you can. But having an analog filter before is still a good idea, even if you have a high sample rate, because there could be some really high frequency noise in there that could get aliased in. And if you don't have an analog filter, you can't be confident that it's not in there. And here's the thing. So it's always advisable to do a low-pass filter that cuts off your signal at, so the idea of a low-pass filter is that lower frequency stuff passes through it, higher frequency stuff gets filtered out. Real filters really just attenuate high frequency stuff. It doesn't make it go to zero, and it just makes it small. And if you have some, you're going to always have some aliasing, even if you have a filter in there. The high frequency stuff will come in, but it'll just be really, really small, and it'll be negligible for your size of your signal. So most of the time, you can just get away with putting on some pedestrian filter. And we're going to talk more about filtering later, so I'm not going to go into the details of filtering now. But filtering is a key aspect of taking good measurements. Okay. All right. So that's the idea with filters and aliasing and Nyquist sampling theorem and anti-aliasing and filter. Okay. All right. And I would also say, even if you think, oh, this signal is not going to have any high frequency stuff in it. It's high frequency noise is so easy to leak into things, and it's hard to get rid of unless you just filter it. Trying to just get rid of the source of it is difficult. Almost always the best thing to do is just to filter. And filtering is cheap. So those RC circuits that we've done analysis on in mechatronics? One of those will have this function. So you could just throw in an RC filter. It's not going to be an awesome filter, but it'll do the job for some really high frequency stuff. It'll do the job. So the only thing that you have to do is choose your R and your C so that you don't filter out the signal you want and you do filter out the stuff that's too high. And it's always dependent on what your sample frequency is. The higher sample frequency, the less filtering you need. But it's always a good idea to have it. Okay, so that concludes. Any questions on that before we move on and do some homework discussion?
What was the not case again?
Yeah. So the not case was, this was the requirement to have a greater sampling frequency than this sampling frequency, 2 times the max, if you want to unambiguously reconstruct your original signal, which is to say, if you don't want to have to worry about aliasing. But the not is that you have aliasing, and this condition is not met. That's right. So this is the, if you wanted to say, what is the condition for your sample frequency? It has to be greater than 2 times F max would be a way to write it in symbols.
Thank you.
Sure. Fn is what we call 2 times F max, so you could also write this Fs is greater than Fn. Nyquist frequency just says this is that magic frequency above which you must sample, but also you don't know where I am. Little caveat. Yeah. All right. So yeah, it's easy to slip back into philosophy all the time in this class. It's great. So that concludes sampling in that discussion.